everybody, and welcome to today's edition of the Spectral Geometry in the Clouds seminar. Today, it's our great pleasure to have Francesca Bianchi from the University of Parma, who will talk to us about the first eigenvalue of the fractional Laplacian for planar sets with topological constraints. So as usual, if you have questions during the talk, you can just unmute yourself and ask them or ask them in the chat. Francesca, the floor is yours.
Thank you. Good morning or good afternoon, depends on where you are. First of all, I would like to thank the organizers for this kind of invitation. During this year, I followed a lot of spectral geometry in the cloud seminar, and I found them so interesting. So it's a pleasure for me to be here and talking about my research topic. Today, I will talk about some estimates of the first eigenvalue of the fractional Dirichlet-Laplacian for some sets in the plane in which we need to do some topological constraints. So the class of the set is related to some geometrical properties of the set. The talk will be divided in two parts. The first part is a recording of some classical results, and I will give you some idea of the proofs. And then in the second part, I will talk about the existence of a fractional counterpart of these classical results. And the second part is based on two papers that are in collaboration with Lorenzo Brasco. I think that I can start with the local setting. So we take omega an open set of the space Rn, and I define the quantity lambda1 of omega as the infimum on the function u in the space W1 to 0 of omega of the Rayleigh quotient given by the square of the L2 norm of the gradient of u over the square of the L2 norm of the function. And this quantity is called the first eigenvalue of the Dirichlet-Laplacian of omega when there exists an admissible function which obtains the value. So if it represents a minimum. And the name follows by the fact it coincides with the smallest lambda such that the differential equation minus Laplacian of u equal to lambda u admits a non-trivial weak solution. Okay, we know that in general the lambda1 of omega for a general set cannot be computed. So we need to find some estimates of that quantity. And due to the fact that it is defined as an infimum, the other estimate is the lower bound. We are interested in finding lower bounds of lambda1 in terms of a geometrical quantity that is the radius, where the radius is the radius of the largest ball that we can put inside our set omega. So this is okay. Another feature is that lambda1, it is well known that rescales as a length to the power of -2. So we expect in our estimate to find the radius to the power of -2. Another quantity that another function that I will use during my talk is the distance function. So I recall now the definition, and it is defined as the infimum of the modulus of the difference between the point x minus the points y that are in the boundary of the set omega. And okay, only a remark is that if omega is regular enough, the radius coincides with the L infinity norm of the distance function. So in general, the radius is greater than or equal to the distance of a point with respect to the boundary of omega. Okay. In general, we cannot find a lower bound in terms of the radius for the quantity lambda1. And a classical example is the set omega defined as all the space Rn with n greater than 1, in which we remove the point Zn. Indeed, in such case, the radius is fixed and it is the quantity in the slide, but lambda 1 of omega is equal to lambda 1 of the whole space Rn, and it is equal to 0, because if n is greater than 1, lambda 1 does not see if we remove a point on a set, so we have that identity. So in this case, we cannot bound from below lambda 1 in terms of the radius. This means that we need to put some constraints on the set that on the class of the set that we are working in. I think that the first result in this way is due to Herschel and Protter, and the first author in 1960 shows that if omega is an open planar in an open planar convex set, then lambda 1 of omega is greater than or equal to pi to the power of 2 over 4 multiplied by the radius to the power of -2. And he have also shown that the strip reach the constant in the slide, so our constant is sharp. Protter, some years later, in 1981, generalized the result to any dimension. But we are interested in a more general class of set. For example, the simply connected one. And in this direction, several authors in the last century showed this kind of result. I refer to this inequality as the Mackay-Hyman inequality later. So the result is that if omega is an open planar simply connected set, then there exists a positive constant such that lambda 1 of omega is greater than or equal to the constant over the square of the radius. And the determination of the sharp constant in this inequality is still an open problem. But as I told you before, several authors looked for this kind of result in the last century. And now I show you some of that references. I think that the first one was Mackay, who in 1965 shows the inequality with a constant of 1 over 4. Its proof was based on 3 points. It uses a Quaria formula. Thanks to this, he moves to a coordinate system given by a variable theta, which fixes the level set, and a variable s, which measures the arc length of the level set. And thanks to the Quaria formula, it shows an isoperimetric inequality with a remainder term, and this isoperimetric inequality is a Bonnesen type inequality. And finally, he found a lower bound in terms of the radius of this remainder term, and these are the main points of its proof. But I recall that his proof was based on a Quaria formula, so it is a strong result that cannot be generalized to other settings, for example, to the fractional one. So we need to add another idea of proof. For example, the Mackay's one. Mackay in 1978 shows the same result with a worst constant of 1 over 900, but its idea of proof was stronger and can be generalized to other settings, and for example to the fractional one. It was based on 3 points. The first one is a geometrical fact, and it is a covering lemma with boundary disks which do not overlap too much. And with boundary disks, we mean some disks centered on the boundary of the simply connected set omega, with the radius fixed and comparable with the radius. And thanks to the fact that they do not overlap too much, he can focus his attention only on one disk, and in each disk he uses the polar coordinates, and for every fixed row he reduces his problem in showing a one-dimensional Poincare inequality for functions that are periodic and which vanishes in a point. And in this part, he uses the properties of a simply connected set. Okay, this is the idea of Hyman, and it can be generalized also to the fractional Sobolev space. But I continue with showing you other references, and for example, the Ancona's one. Ancona in 1986 shows the same inequality with a constant of 1/16, and his proof was based on an archetype inequality where the distance is given by where the weight is given by the distance of the point with respect to the boundary of the set. In order to show this inequality, he uses conformal maps, and thanks to the relation between the distance function and the radius, he can bound from below the right-hand side in this way. So he also found the Mackay-Hyman inequality with a different proof and with a different constant. The last result about simply connected set that I will show you today is due to Banuevas and Carroll in 1994. I think that it is the best result in order to find the sharp constant of the inequality, and they show that the sharp constant is in the interval in the slide, and in order to show the upper bound, they choose properly a test function and they bound from above. And in order to find the lower bound, they use a stochastic approach. Okay, these are 4 of the references about the Mackay-Hyman inequality. But if we are interested in a more general class of sets, I think that first of all, I have to give some definition. Okay, we take omega an open planar connected set, and I call it multiply connected set of order k if its complement in the Alexandrov compactification has k connected components, where the Alexandrov compactification is the whole plane R2 in which we add a point at infinity. So our sets are open, planar, connected, and in our set we do k-1 poles. So we remove k-1 connected sets. And for this kind of set, there exists a result similar to the previous ones. And Osserman in 1977 shows that if omega is an open planar set as in the definition, then there exists positive constant such that lambda1 of omega is greater than or equal to this constant over the radius to the power of -2 multiplied by the by k to the power of -2. So now the constant depends also on the parameter k. 2 years later, Taylor improves the dependence on the parameter k of the constant by showing the optimal dependence, that is k to the power of -1. And finally, Crook 2 years later shows the same result by founding an explicit constant, that is 1/2. And we know that this constant is not sharp, and the case k equal to 1 covers the simply connected k. Let us look to the main idea of their proofs. The proof of Osserman is based on a Cheeger inequality, where the Cheeger inequality compared the lambda1 or the root square of the root of lambda1 with the Cheeger constant that is defined as the infimum valued on the subset omega prime of omega of the quotient given by the perimeter of omega prime over the volume of omega prime. Okay, the second step is an isoperimetric inequality of boundness and type, so with a remainder term, and as Hersch did, he estimates the remainder term in terms of the values. So these are the three main points of the Osserman estimate, and this is all. But we know that it's dependent on the parameter case, not optimal. So let us look at the main points of the proof of Taylor. The first step is a geometrical fact, and it is a tiling lemma with squares, which contains a Dirichlet region. Where with Dirichlet region we means a region that is in the square, and it is also in the complement of omega. And due to the fact that our function vanishes outside omega, in this region, in this compact, our function vanishes. So this is the reason of the name. And the second point is a Poincare inequality for this square. I will enter more in details of its proof later, so I think that for now it is enough. Finally, Crook in 1981 refines the Osserman argument by founding the optimal asymptotic behavior of on the dependence of K of the constant, only using the Osserman argument. I think that for the local case it can be enough. So let us move to the fractional setting. And in order to do it, I recall you some definition that I think that most of you already know. We take S between 0 and 1, and we call the Gallardo-Slobodevsky seminorm as the quantity given by this W integral. I only observe that the W integral is done on Rn times Rn. Okay, with this seminorm, I can define the fractional norm that we use, and it is given by the sum between the Gallardo-Slobodevsky seminorm and the H norm of the function. And with this norm, we set our fractional Sobolev space defined as the closure of the function in C infinity 0 of omega with respect to the norm that I still show you. Okay, I recall you that in the first part of the talk, I defined the quantity lambda 1, and I show you the relation between lambda 1 and a PD, where in the PD it appears the Laplace operator. So now I define the fractional counterpart of this operator, and it is the fractional Laplacian of order S of the function u, and it is defined as in the slide. It is well known that the Laplace operator is a local operator, while in this case our operator is non-local, where with non-local we mean that the fractional Laplacian of order S of the function u in the point x depends on the behavior of the function on the whole space Rn. So many estimates and property which works in the local setting now cannot. As in the local case, now I define the quantity that we will estimate, and it is lambda 1s of omega, and it is defined as the infimum on the function in the fractional Sobolev space that I defined before of the Rayleigh quotient that is similar to the previous one, but now the H norm of the gradient of u is replaced by the Gallardo-Slobodevsky seminorm. And as in the previous case, we call it the first eigenvalue of fractional Dirichlet-Laplacian of order S when there exists an admissible function which reach the value, so if it represents also a minimum. And the name follows by the fact that it coincides with the smallest lambda, such that the equation minus Laplacian minus fractional Laplacian of u equal to lambda u admits a non-trivial mixed solution. Okay, now our quantity due to the scaling properties of the Gallardo-Slobodevsky seminar and of the H norm of the function, rescales as a length to the power of minus 2s. So in our estimate, we expect to find a power over the radius of minus 2s. The first well-known result that I show you today is due to Burgen-Mrzise-Mironescu, and it is in a paper of 2001, and they show that for every open set omega in a Rn and every function u in simping 0 of omega, we have that the limits as s goes to 1 of 1 minus s multiplied by the square of the Gallardo-Slobodevsky seminar is equal to the square of the H norm of the gradient of u up to a multiplicative constant which depends on the dimension n. And this result means that the Gallardo-Slobodevsky seminar is an extension of the square of the H norm of the gradient of u. So it means also that in our constant we expect to find a term in as 1 minus s near our constant. Now I give you the last definition of the talk, and this notion is useful in our proof, and I think that it is the key point of to show the existence or the non-existence of the fractional counterpart of the previous result. So we take s between 0 and 1, and omega an open set that I refer about omega as a box. We also take sigma as a compact subset of our set omega, and we define the fractional capacity of the compact sigma of order s with respect to the box omega as the quantity, as the infimum of the square of the H norm of the Gallardo, as the square of the Gallardo-Slobodevsky seminar with respect to the function which makes which are 1 or greater than 1 over the compact sigma. I observe that the W integral also in this case are given on the whole space Rn. So the box appears in the choice of the admissible function, because we require that our function vanishes outside our box. Okay, with this notion, I show you a previous result that we have proved. It is a one-dimensional fact. We have shown that if s is strictly greater than 1/2 and that 0 is a point in an interval AB, then the fractional capacity of the point with respect to the interval is greater than or equal to a constant which depends on s multiplied by the length of the interval up to a negative power. And we have also studied the asymptotic behavior of the constant as s goes to 1/2 and as s goes to 1. Okay, we know that the right-hand side of our inequality is strictly positive, and it is important because thanks to a result of Abatangelo, Pelli, and Norris that in 2020 showed that for every open bounded box omega and every compact subset k of omega, lambda 1 s does not change if we remove the compact, if and only if the compact is small enough, where with small enough we means that its capacity with respect to the box is 0. So coming back to our result, due to the fact that our capacity of the point with respect to the interval is strictly positive, we means that if we remove a point from an interval, the lambda 1s will change. Okay, this is our result. Let us look to the main idea of the proof. Due to the fact that we are in the linear case, we can take the Fourier transform, and thanks to the Plancherel inequality that also for the Gallardo-Slobodevsky seminar, we have shown this inequality. And by doing some computations on this integral, and by taking t inside of the interval and tau outside of the interval, we have shown this Morrey-Sobolev inequality. And finally, by recalling that by definition of capacity, we need to ask that phi valued on x0 is greater than or equal to 1, we can conclude by taking the infimum over the admissible function phi. So we have the thesis of our lemma. Okay, now I think that we are ready to show our main result. This is okay. This is the result. We take S strictly greater than 1/2 and omega as a planar open multiply connected set of order k with the finite radius. We have shown that there exists a positive constant theta S, which depends on S, such that lambda 1s of omega is greater than or equal to theta S over k to the power of S multiplied by the radius to the power of minus 2s. Moreover, we have studied the asymptotic behavior of the constant as s goes to 1/2 and as s goes to 1. The asymptotic behavior follows from the previous lemma, and okay, it happens what we expect, because as s goes to 1/2, the inequality is trivial, while as s goes to 1, thanks to the result of Boulogne, and Mironescu, we have the term that I told you before. So this is the term that we expect to find, but I will talk about it in the last slide, I think, in one of the last slides. Now, as I told you before, let us recall the main points of the Taylor's proof in order to adapt and to generalize its idea to the fractional Sobolev spaces. I recall that the first point was a tiling lemma with the squares containing the Dirichlet region, while the second part was a Poincare inequality for this square. And now I write in the slide also the right Poincare inequality, and we can observe that in the constant it appears a capacity term. So the last part is to find a lower bound for the notion of capacity. In order to move to fractional Sobolev space, the first point is still the same. So we have shown the tiling lemma with this kind of square. The second point is a Poincare inequality, but now the L2 norm of the gradient of u is replaced by a semi-norm. And in this case, the integrals are given only on QL times QL, and the capacity is replaced by the fractional capacity. So the third part is an estimate, a lower bound for the fractional capacity of our sigma. Let us enter more in details in these 3 points. Okay, the tiling lemma allows us to tile the whole plane with the squares, where the length side of the square is equal to the root of k multiplied by the radius up to a multiplicative constant. And thanks to the choice of this L, we can assure the existence in each square of a compact set in the complement of omega. So as I show you in the picture, in each square there is a compact that is in the complement of omega, but it is also in the square. And okay, but now we observe that we can write the Gallardo-Slobodevsky seminorm, so the integral on R2 times R2, as a numerable sum of this W integral, given only on QLI times QLJ. But we can bound from below this sum by taking only the integral on the diagonal. So by taking only the W integral of QLI times QLI. And this means that we can focus our attention only on one square QL. So in each square we have a Dirichlet region, and we are sure that this compact sigma is fat enough, where with fat enough we means that the capacity of that set is strictly positive. But it is easy to work with a one-dimensional set. Indeed, we have the one-dimensional lemma and these kind of things. So we try to move to one-dimensional set by taking the projection on one of the two axes. So we have also shown that fat enough, requiring that our compact is fat enough, means that almost one of the two projections of our compact sigma, that in the picture is the black set, is greater than or equal to L up to a multiplicative constant. In this part, we have used the definition of the radius and of multiply connected set of order k. Now we are ready to show the second part of the second step of the proof, that is the Poincaré inequality for the square. And the inequality is the one on the slide. The term of 1 over the square of L appears only due to the scaling properties of the fractional capacity of the semi-norm and the H2 norm of the function. And let us look the main idea of the proof of this Poincaré inequality. First of all, I observed that the capacity, the box in which we value the capacity, is enlarged with respect to our square. This is the reason is that we need that our sigma has to be well contained in the box. So we have to enlarge the box, and in order to do this, we need an extension operator which compares the semi-norm with the semi-norm and the H-norm with the H-norm. So we have shown the existence of this operator. The second step is a properly chosen test function for the notion of fractional capacity, while the third step is a fractional Poincaré-Wirtinger inequality for a function with zero average. So with this notion, with this notation, we mean the average of u on a ball of radius 3l. So with these 3 points, we have shown the Poincaré inequality for squares, and I think that we use it a classical way to show this kind of estimate. Now we have also shown the second part, so it remains only to bound from below this capacity. And in order to do this, we use the one-dimensional lemma that I showed you before. So we use a dimensional reduction in order to move to the one-dimensional case. And we have shown the inequality in the slide. And now, by construction, the distance between the compact sigma and the boundary of the ball is comparable with the length L. So we can bound from below this term with L to the power of 1 minus 2s. And by using the tiling lemma, that was the first point of our proof, we can bound from below the maximum of the two projection with L. So we can conclude by taking all the points together that for every square QL, we can bound from below the square of the semi-norm of U with this term, thanks to the second point. And thanks to the third point, we can bound from below the notion of the capacity with this one, and we have shown the inequality. By recalling the choice of the length side L, we have the thesis. This is the result about the existence of the fractional counterpart of the Taylor, Crook, and Osserman result, but I observed that we need to ask that S is strictly greater than 1/2. So now I talk about the optimality of our estimate. We have shown that why we need the restriction on S that is strictly greater than 1/2, because we have shown that if S is less than or equal to 1/2, there exists a sequence of open bounded simply connected sets with uniformly bounded from above and from below, such that the limits as n goes to plus infinity of lambda 1s of our sequence goes to 0. So for this sequence, we cannot bound from below lambda 1s in terms of the radius. And the shape of this sequence is given by an enlarging square in which we do some cuts. So as n goes to plus infinity, our square covers all the plane, but the distance between the cuts remain the same. So the radius does not change, is fixed and does not change as n goes to plus infinity. But with this choice of S, the capacity of a segment and of a line with respect to a b-dimensional set is equal to 0. So the Gaillardo-Slobodevsky seminar and also lambda 1s of the lambda 1s will not see if we remove the cut, and this is the reason for the main idea under this counterexample. So with this choice of S, we cannot show the existence. We have shown the non-existence of the fractional counterpart of the previous result, but now it remains only to discuss about the optimality of the behavior of the constant. Okay, our constant is not sharp because the sharpness is unknown also in the local case. So we cannot hope to find the sharp constant, but we can discuss about its dependence on the parameter S and on the parameter K. So we have shown that for every open planar set, lambda 1, the classical one, lambda 1 of omega is greater than or equal to the lim sup as S goes to 1 of lambda 1s of omega multiplied by 1 minus S up to a multiplicative constant. But thanks to our main result, if omega is multiply connected set of order K, we can bound from below this this product, and if we take the first and the third terms of this chain of inequality, we found the Osserman, Taylor, and Crook result. So it means that the dependence on the term 1 minus S of our constant is optimal. And what is the idea of this of the proof of this part? I recall you the result of Burgani and Mironescu, which shows this identity, and so we can okay, if we take the lim sup as S goes to 1 of 1 minus S of lambda 1s of omega, and we take an admissible function u, we can bound from above with this quotient. But now, thanks to the result of Burgani and Mironescu, we know that this limit is equal to this Rayleigh quotient by taking the infimum over the admissible function u of lambda 1. We have the thesis. So we have the optimality with respect to the S goes to 1. but we have also shown that if S is strictly greater than 1/2, then there exists a sequence of multiply connected set of order k with the uniformly bounded radius, such that the lim sup as k goes to plus infinity of k up to the power s multiplied by lambda 1s of omega k is finite. And it means that also the dependence on k of our constant is optimal as k goes to plus infinity. And how is the shape of our sequence? Okay, we take a bounded set. The shape of this set is only to assure that the holes are k minus 1. So we take a bounded set, and we remove k minus 1 points that are for which the distance from each other is the same. So by doing some computations, we have our result. And the last part is that for every k strictly greater than 0, we have shown that there exists a multiply connected set of order k theta k with finite radius, such that the lim sup as s goes to 1/2 of the quotient given by lambda 1s of theta k over 2s minus 1 is finite. And okay, this means that also the dependence on the term 2s minus 1 is optimal as s goes to 1/2. So in this way, we have shown the optimality of our constant. The shape of this set is given by, okay, we take the set of the previous counterexample. So we take the whole plane R2 and we do some infinite cuts that are these in the picture. And we also remove k minus 1 points that are distant with the same distance, one from each other. And by doing some computation on this set and by taking properly the cutoff function, we have shown this that this lim sup is finite. I think that it can be enough. So I thank you for your attention.
Thanks a lot, Francesca, for your talk today. I think we have some time for questions now, so you can either unmute yourself or ask them in chat. So I'll so the fact that you look at these quantities in dimension 2, is it for simplicity, or they don't make sense in the same way in higher dimensions?
Okay, for higher dimension, the key point is that if we remove a segment in higher dimension, the capacity is 0. So we cannot show the existence of this kind of result to higher dimension. We need to put also about the p, so we cannot take p equal to 2, and we have to change something because it cannot hold in higher dimension. Because we can make some counterexample by doing a lot of cuts, and the capacity, the lambda 1s in higher dimension will not change if we do some cuts, and we can show a lot of counterexample with offsets with finite in radius and with covers all the space Rn.
Hi, maybe I have a question.
Yes, Doreen.
In higher dimensions than 2, so somehow an equivalent quantity to which one may look instead of simply connectedness is the capacity density condition. So it's the ratio of the capacity of the complement divided by the ratio of the ball, whether it is uniformly bounded from below in some sense, you get sort of similar behavior as simply connectedness in two dimensions. Do you have an idea on that?
Okay, we have not looked in this way, but so I think that we need to change the notion of the radius or the notion of simply connected set, because we have to relate the constraint with the capacity of the set that we are removing.
Thank you, Doreen, for the question. Do we have other questions for Francesca?
I have a small question.
Yes, go on.
I couldn't really follow. We are not assuming that the sets are bounded, or are we?
No, the set is not bounded. It can be unbounded. The only requirement is that the radius has to be finite.
Or okay, and then okay, maybe this is related, but when you introduced so this number of connected component k,
Yeah.
This is why you considered the compactification of Rn to allow for unbounded sets.
No, the compactification, we take the compactification only to have the notion of multiply connected set of order k well defined, because okay, here, okay, because no, because in this way, okay, I think that in this way, if we take the strip, if we don't take the compactification and we take this strip, we have that its complement as two connected components, but the strip, the infinite strip, is a simply connected one. So we have that it is so in this case k has to be equal to 1.
Okay, so with your definition,
yes.
K is equal to 1 for the infinite strip, for instance.
Yes, for the simply connected set.
Okay.
So it is only to have to be coherent with the definition, but if we take only the plane without the compactification, we have some changing in the dependence on k, but the argument works also without the compactification.
Okay, thanks. The examples makes it.
I have another question myself. So do we have an idea of what's the behavior in S really between a half and one? Do we expect that, for example, some sort of convexity or concavity, I guess, in this?
I don't understand.
So you have this function theta s, right? That appears in your bound. And you know that at 1/2, it looks like 2s minus 1, and it looks like 1/1 minus s at. But do you expect? So it sorry, it interpolates between 0 and I guess in infinity, but do you expect to have any sort of to know that it's an increasing function of s, or
okay, we don't know it. I don't know what can be the behavior of the constant with respect to s. No,
I think it would be, I mean, quite natural to expect that it has to be increasing, or at least non-decreasing, right?
Yes, I think so. I think so, but we have not looked about it. Yes, I expect that it is increasing also thanks to this asymptotic behavior, but I'm not sure.
All right, maybe we have time for other questions if there's some. All right, otherwise, let's thank Francesca again, and we will.